What's up, everybody, and welcome back to OpenStax Algebra and Trigonometry, Chapter 5, Practice Test. Let's do it. For this question, it's asking to find the degree and the leading coefficient. Now, before we can do that, we have to distribute this and simplify a little bit. So we're going to distribute that x cubed. So now we have 3x cubed minus 6x times x cubed is 6x to the fourth. And then negative 2x squared times x cubed is negative 2x to the fifth. Now we're going to rearrange it in order of degree. So greatest degree first. So it's going to be negative 2x to the fifth minus 6x to the fourth plus 3x cubed. And this is my leading term. It's the term with the highest degree. So the degree is that exponent. The degree is 5. And then the leading coefficient, is that number in front of that term. So the leading coefficient is negative 2. So those are your two answers. 5, negative 2, done. So for this one, when we're talking about the end behavior, the first thing I want to do is I want to simplify. So I want to distribute this, and then I get negative 8, right? 4 times negative 2 is negative 8x squared. Negative 3x times that is positive 6, and then x cubed, right? X squared times x is x cubed. And then negative 5 times negative 2 is positive 10. X squared times x squared is x to the fourth. Okay, the reason why we do this is because now I can write this in order from the greatest degree down to the smallest degree like so in this nice standard form. And then we can look at our leading term because that's going to tell us the end behavior. So since the degree is even and the leading term, the leading coefficient is positive, okay? So even positive means that this graph is going to look like there could be stuff in the middle, but the bottom line is on the edges, it's going to go up and up. That's when you have an even degree and a positive coefficient. So what does that mean? It means as x goes towards negative infinity, meaning as we go to the left, right out here, where's the function going? It's up, meaning the function value is approaching positive infinity. And then as x approaches positive infinity, meaning as we go to the right, again, the function value is approaching positive infinity. It's going up. So there's your end behavior done. For this one, we know the vertex and we know a point on the graph. So we're going to start with vertex form, aka standard form of a quadratic, which is a times x minus h squared plus k. And since we know the vertex plugs in for h and for k, right? So now we have y equals a times x minus 2 squared plus 0 for k. So I don't need to write that. And then the question is, what is that a term? Well, they give us another coordinate, which is 4, 12. 12 is the y value. 4 is that x value. So if I plug and chug, I can solve for a. So I got 12 equals a times 4 minus 2, which is 2 squared, which is 4. Divide both sides by 4, and we get a equals 12 over 4, which is 3. So now if I want to rewrite this one last time, coming from here, plugging in 3 for a, I get y equals 3 times x minus 2 squared. There it is, done. So for this one, we're meant to find the zeros and noting the multiplicity. So first of all, this is nice because it's in factored form. So I've got 3 locations where I can find zeros for this function, aka values of x, that when I plug it in, it zeroes out the function value. So this one, I can tell it's 3 because 3 minus 3 is 0. So I've got a 0 at 3. And what about the multiplicity? That is determined by the exponent of that binomial. So 3 with a multiplicity of 3. In here, what's going to zero this out? It's going to be 1/3. 1/3 times 3 is 1 minus 1 is 0. So 1/3, and since there's an invisible 1 as an exponent, the multiplicity is simply 1. Last but not least, what's going to zero this out? That's going to be positive 1, right? 1 minus 1 is 0. And since it's squared, it's going to have a multiplicity of 2. Boom, done. For this one, we're going to find the zeros and the multiplicities based on the graphs. So first, we're starting with zeros, aka x-intercepts. Where is it hitting this x-axis? So I see that first it looks like it's hitting it at negative 1/2. And then when it comes to the multiplicity, the fact that it's penetrating, it's not bouncing, it's going through, indicates that it's an odd multiplicity. So we could say it'd be a multiplicity of 1, 3, 5, something like that. But because it kind of flattens out like this, it doesn't just kind of go straight through. Because it flattens out, that's an indication that it's going to be greater than 1. So maybe 3 or 5 or 7. But we'll just roll with that bare minimum of 3, something greater than 1. And then what about this one? We have another 0 at 2. So that is good. But now when we're talking about the multiplicity, it's bouncing, which means it's not an odd multiplicity. It's an even multiplicity, like 2, 4, 6, 8. And we'll just roll with the lowest of those, which is a multiplicity of 2. Boom, done. For this one, we're going to run synthetic division to find the quotient, and we're going to start with the opposite of that -2, which is 2. That's, from the divisor, we throw that in the box. Then we're going to list the coefficient of the numerator, aka the dividend. So we got 1x to the fourth, 0x cubed, because there's no x cubed, 3x squared, 0x, because there's no x term, and then -4. So now let's run it. So we get a 1 multiplied by 2, right? We just drop the 1 times 2 is 2, 0 plus 2 is 2, times 2 is 4, 3 plus 4 is 7, 7 times 2 is 14, 0 plus 14 is 14, and then 14 times 2 is 28. We add those together and we get a remainder of 24. So the quotient, though, however, is going to be this part, 1, 2, 7, 14, starting with x to the third, because we're dropping by 1 degree from where we started. So 1x cubed plus 2x squared, we kind of waterfall down, then plus 7x to the first plus 14. And then last but not least, we take that remainder and we throw it on top of the divisor, on top of that original denominator of x minus 2, and there's your answer, done. So here we're going to use the rational zero theorem to help us find the zeros, and the rational zero theorem says that the rational zeros are going to come from a ratio of factors of this last term divided by factors of that leading coefficient. So the factors of 9 are, and it's negative, but again, we're doing plus or minus, so it kind of doesn't matter the sign. It's going to be plus or minus 1, plus or minus 3, plus or minus 9. And for that first term, 1 and 2 are the factors. And so now it's going to be 1, 3, and 9 all divided by 1, which is just 1, 3, and 9, or 1, 3, and 9 divided by 2, which also includes 1/2, 1/3, and 1/9, which also includes 1/2, 3/2, and 9/2. And these are all plus or minus, right? So this is the possible list of rational zeros. And then to test which ones are the actual zeros, we're going to have to start plugging and chugging. So we'd be like, all right, first let me maybe start with 1, then -1, 3, then -3, etc. So these are all the options. And let's say we try 1 and we plug it in, we should get a remainder that is not 0, which means 1 doesn't work. The one that will work is when we get a remainder of 0. So let's pretend we tried 1. Now we're going to go ahead to -1. Hint, hint, I do know that -1 works, but we're going to skip the ones that just show that it's incorrect. So plug in -1, we got the synthetic set up with the coefficients 2, 5, -6, and -9. And then we run synthetic, so we drop down the 2. 2 times -1 is -2, plus 5 is 3. 3 times -1 is -3, plus -6 is -9. -9 times -1 is +9, plus -9 is 0. And now we know we've done it correctly. That means indeed -1 is a 0. Now we get to this point and we've only got 3 terms left. So I can keep running synthetic division with these other values to find it. But when we just have 3 values like this, it's actually easier to recognize that this is now 2x squared plus 3x minus 9. That's a trinomial, and that means we can actually factor this, and I'm going to do so using the star method because we got a leading coefficient, an a value that's greater than 1. So we got a goes here and here for the star method, a times c, 2 times -9, -18 up top, and then 3, the b down here. So what two numbers multiply to -18, add to +3? That'd be +6 and -3. Then I reduce this like a fraction to make that 1/3. And now these are the coefficients of the factored binomial. So it'd be 1x plus 3 times 2x, right? The 2 goes with the x, and then -3 over there. So now we have our other two zeros. When is this going to zero out? At -3. When is this going to zero out? At +3/2. And then we already have the -1 from before. So here are your 3 solutions: -3, 3/2, -1, boom, done. For the next one, we're going to start with the rational zeros theorem and start with all the factors of 18 divided by all the potential factors of 4. So 18, we have 1, 2, 3, 6, 9, and 18, all plus or minus. And then for 4, it's 1, 2, and 4. So that's going to give us a bunch of different possibilities. We have 1, 2, 3, 6, 9, 18 divided by 1, so that's just as is. Then we have all of them divided by 2, so we'd also have 1/2, 3/2, 9/2. 18/2, 6/2, those wouldn't matter because those would repeat as 3 and 9. And then last but not least, everything divided by 4, 1/4, 2/4, which is 1/2, 3/4, etc., etc. We have a huge list. And then now what we do is, as we apply this, we'd run these through in some order into synthetic division to see when we get a hit, aka to see when we get a remainder of 0. That tells us that we've gotten a correct 0 for this rational 0 for this polynomial. So I'm going to jump ahead with a little forethought, and I'm going to say, okay, we're going to jump into 1. I usually do start with 1, but I'm starting with 1 because I do indeed know that it's going to work. And I'm going to show you what it looks like when you get a match, when you get something that works. So again, we got the coefficients in order of degree. So 4x to the 4th, 16. Then we got 13, negative 15, and negative 18. And then we're going to run it by dropping the 4. 4 times 1 is 4, plus 16 is 20. 20 times 1 is 20, plus 13 is 33. 33 times 1 is 33. Plus negative 15 is 18. 18 times 1 is 18, plus negative 18 is 0. Boom. So indeed, 1 is a nice 0 of the function. Now we're going to run it again. So, we're not down to the place where we only have 3 numbers and it's a quadratic and we can factor. So we're going to have to run it again. So now, maybe we try -1, maybe we try 2, and then maybe we get to -2. So let's go through with -2 again. I'm choosing -2 intentionally because I do know that it's going to work. But the other ones where it doesn't work, you get a non-zero remainder. Now we're going to see what happens with -2. So we drop the 4. 4 times -2 is -8. 20 plus -8 is 12. Times -2 is -24. Plus 33 is 9. 9 times -2 is -18. Check it out. That zeroes out to a remainder of 0. So now we have 3 terms. Now we can write this as 4x squared plus 12x plus 9, and we can see if this is factorable. And guess what? We can do that using the star method because we got an a value that's greater than 1. So we got a going here and here. A times c, 4 times 9 is 36 up top, and then 12, which is the b term down here. So what 2 numbers multiply to 36 add to 12? That's 6 and 6. Simplify like a fraction. That's 2 and 3 on both sides, like so. Boom and boom, which means this factors to 2x plus 3 times 2x plus 3. All right, so that's going to be the same 0. What's going to zero this out? That's -3 over 2, right? Times 2 is -3 plus 3 is 0. So we got -3 over 2. And since it's occurring twice, right, it's really 2x plus 3 squared. That's a multiplicity of 2. And then the other ones are just occurring once. We have also 1 and -2. Those both have just a multiplicity of 1. So these are your zeros. Done. So here we're trying to find the polynomial given that this is a double 0 at 3, and then we just have a regular 0 at 1 and -2, plus a y-intercept. So I'm going to start it out as follows. Since I have a double 0 at x equals 3, that means x minus 3 is one of the factored binomials. And that double 0 means a multiplicity of 2, aka we have an exponent of 2. Then we also have a 0 at x equals 1, aka x minus 1 is a binomial, and x equals -2, aka x plus 2 as a binomial. And then there's also going to be an a term. Okay, we don't know what that a term is, but the a term is going to be found using this nice y-intercept. So what we're going to do is we're going to plug 0 in for x and 12 in for y and solve for a. So 0 minus 3 is -3 squared is 9. 0 minus 1 is -1. 0 plus 2 is 2. This gives me 12 equals a times 9 times -1 times 2 is -18. Divide both sides by -18. A equals 12 over -18, aka -2/3. Last but not least, we can rewrite this nice polynomial by plugging in the -2/3 for a. So we got -2/3, and then we'll leave the rest as is. And here is your final answer. Boom, done. So we're going to use Descartes' rule of signs to determine the possible number of positive and negative solutions. So for positive, I'm going to take the function as is and look at the sign changes. So I go positive to negative, that's 1, and then negative to positive, that's 2. So we've got 2 possible positive solutions, or we also can drop that down by 2 to 0. And we can't go anymore, right? You can have -2 solutions. So we either have 2 or 0 positive solutions. And then for the negative, we start by plugging in -x for x. Then we have -x cubed is -x cubed, so it's -8x cubed. -x in here for x squared, it'll just square the -x and it'll stay as is. So nothing changes there. And then the 6 stays as is. So we see negative to negative, no sign change, then to positive, that's 1 sign change. So there's 1 negative solution here and 2 or 0 positive solutions, boom, done. So for this one, before we start, we're going to factor that numerator. So what two numbers multiply to -3 add to +2? That's +3 and -1. And I'm going to factor the denominator as well because it's a difference of squares. X minus 2 times x plus 2. All right, so now that we have it factored, it's going to be pretty easy to come up with our vertical asymptotes. It's going to be where we're going to zero out the denominator, and that's going to be at x equals +2 and x equals -2. For the horizontal asymptote, since we have in our original the degrees being the same for the top and the bottom, both to the second degree, we take the ratio of those two leading coefficients, 1/1, and set that equal to y. So my horizontal asymptote is y equals 1. And then if we're talking about the intercepts, so the x-intercepts are where we're going to zero out the denominator and get 0 for a function value. So that's going to occur at -3, 0 and +1, 0. Last but not least, for that y-intercept, the y-intercept occurs when x equals 0. So we plug in 0 for x and we get 3 times -1, which is -3, over -2 times 2, which is -4. So that gives us a y-intercept of 3/4. For this one, we're going to start by graphing those vertical asymptotes. So first we have x equals 2, then we have x equals -2. Now we're going to draw in that horizontal asymptote at y equals 1. So that's a nice horizontal line right there. And then we've got those x and y intercepts. So the x-intercepts are at -3, 0, and +1, 0. And then we also have the y-intercept at 0, 3/4, which is going to be right here. So now the only question is this function ever going to cross that horizontal asymptote, which can happen sometimes. Not the vertical, but it can cross the horizontal. So to figure that out, I'm going to set this entire polynomial equal to the value of 1. Then I'm going to multiply out the denominator to the other side. The x squareds cancel out, and then I've got 2x, I'm going to add -3 to the other side. 2x equals -3 plus, 3 plus -4, which is -1. Divide by 2, x equals -1/2. So it looks like it actually does cross that line right here at -1/2, 1. So it's going to cross or touch it there. Now this is interesting because now this gives us enough information to sort of figure out what this is going to look like. On the inside, it's going to go down here, and as per usual, we're going to hug that vertical asymptote. So it kind of looks like it crosses. That's meant to be just over. All right, that looks a little bit better. And then to the left, it crosses here, but it never crosses again. So we can then therefore assume that it's going to go up to the left like this, hugging that other vertical asymptote. And if you're not positive about that, you can plug in -1 and see what you get. You should get something above this horizontal asymptote, so that's good. Now, it doesn't cross it anywhere else, which means we can safely say with this point that it's going to go down, hug that vertical asymptote, go to the left, hug that horizontal asymptote. Now over here, it's either going to be up here or over here, one of the two. And to figure that out, you can plug in any random point. How about plugging in 3? So if I plug in 3, I get 3 plus 3, which is 6, times 3 minus 1, which is 2. So that's 12 over 3 minus 2, which is 1, times 3 plus 2, which is 5. So that's approximately 2.4. So that's for 3. We're somewhere in this zone. So that's up here. And again, there's no other crossing of the horizontal. So we're going to hug that horizontal like that. We're going to hug the vertical as we go up here. And there's your graph. Boom, done. For this one, we're meant to find the inverse of this function. So we're going to start by replacing f of x with y. And then after that, we're going to swap the x's and the y's. So we got x equals radical y minus 2 plus 4. And then now we're going to isolate the y. So I'm going to subtract 4 from both sides like so. Then I'm going to square both sides because we're still trying to get that y out so we can isolate it. Now I have y minus 2 equals x minus 4 squared. And then my last step is I'm going to add 2 to both sides, and then I get x minus 4 squared plus 2. Now to put this in that nice function notation, I got f inverse of x, or f to the -1 of x, equals that x minus 4 squared plus 2. And then the question is there a domain restriction that I have to impose? And I do, because this function here looks like this, right? It goes up like that to the right. And it has a range, okay? It doesn't go below 4 because the lowest this can go is 0, right? 2 minus 2 is 0 plus 4 is 4. So the range is everything from 4 to infinity. Well, I'm going to use that same range as our domain for the inverse, right? The x's and the y's are flipped. So the the domain that I'm going to impose is x is greater than or equal to 4. So here's the inverse with that domain restriction. Boom, done. So for this one, we're going to start by swapping the f of x with y. Then we're going to switch the x's and the y's. So I have x equals 2y plus 3 over 3y minus 1. And now to isolate y, we're going to start by multiplying that denominator to the other side. Then I'm going to distribute, and I got 3yx minus x equals 2y plus 3. Then I'm going to subtract 2y while adding x to the other side. So 3yx minus 2y equals x plus 3. Then I'm going to factor out this y. So that's why I'm getting the y's on the left side. So I got 3x minus 2 equals x plus 3. Last step, I'm going to divide both sides by 3x minus 2. So I get y equals x plus 3 over 3x minus 2. Last step, I'm going to replace the y with that nice function notation. F inverse of x equals x plus 3 over 3x minus 2. There's your answer, done. For this one, it says y varies jointly with x and the cube root of z. So that's like direct variation with both of those. So it's y equals k times with x, right? Jointly with x and the cube root of z. So it's just all one big multiplication string, right? K times x times the cube root of z. Let's put parentheses here so we don't get that confused with x cubed. And then it says when x equals 2, and z equals 27, y equals 12. So that information is good at the beginning because it's going to help us solve for that constant. So let's plug and chug. 12 equals k times x is 2, and then we got the cube root of 27. So the cube root of 27 is 3 because 3 times 3 times 3 is 27. 3 times 2 is 6. 12 equals 6k, divide by 6, k equals 2. Now I can rewrite this direct variation equation as y equals k is now 2 times x times the cube root of z. Last but not least, we need to find y when x is 5 and z is 8. So y equals 2 times x is 5, and then the cube root of 8, because z is 8. The cube root of 8 is 2. So then we got 2 times 5 times 2, which is 20 for the win. Boom, done. I hope you guys enjoyed this video, and if you did, please click that like button. And if you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.